Welcome back. We start this video with this theorem. So any given integer n greater than 1 is divisible by a prime number. So that's the statement. All right, so how do we prove this? Well, if n is already a prime number, then we are done because it's divisible by itself. If it is not a prime number, then it's got to be a composite number, so it has a smaller divisor n1. So n1 is smaller than n and it's greater than 1. So it has some divisor n1 greater than 1. Now if n1 is a prime number, then we are done again because n1 is a divisor of n, so that's going to be a prime divisor of n. On the other, if n1 is not a prime number, then n1 and in turn n has another divisor n2 greater than 1. So we can keep going now, or we can play the same game with n2. Either n2 is a prime, and when we're done, if n2 is not a prime, then n2 has another divisor greater than 1. But this process must stop because this sequence of divisors that we are getting, it's a strictly decreasing sequence of positive integers. So this process must stop. Let's say at the kth step, and we get this integer divisor nk greater than 1, and it doesn't have any more divisors, so therefore nk has to be a prime number. But nk is of course a divisor of, is a divisor of n. So again, the divisor of a divisor of n is a divisor of n, right? So nk would be a prime divisor of n in that case. Okay. This is the fundamental theorem of arithmetic. I'm not going to prove this theorem because it takes quite a bit of time. But you can look it up from from your text or any other. There are many other places you can look it up from. So an integer n greater than 1 can be factored uniquely as a product of prime powers. So n is equal to p1 to the a1 times p2 to the a2 times pn to the an, where p1, p2, pn, this is a increasing sequence of prime numbers, and a1, a2, an, they are positive integers. So let me just explain this theorem by using an example. So if I have the number 12, that's the same as 2 squared times 3. The number 2100, that's the same as 2 squared times 3 times 5 squared times 7. Okay, here is the theorem. It's known as the Euclid's theorem. I mean, there are many other theorems associated with Euclid's name. So it says that there exist infinitely many prime numbers. So why do we have infinitely many prime numbers? Well, suppose on the contrary that there are only finitely many primes. Well, if we have only finitely many primes, then let's say we have n of them. So, and then we can label them as p1, p2, pn, and let's say they are in increasing order. Well, then let's consider the number n, which is the product of this all the prime numbers plus 1. By the fundamental theorem of arithmetic, we know that n must have a prime divisor. And so let's say the prime divisor of n is p, and so p must be among these finitely many primes that we are assuming. Well, let's see. so P must divide, well, since P is among these prime numbers P1 up to Pn, so P must divide the product of these prime numbers. So P divides P1 times P2 times Pn. Well, it then follows that P divides, so since P is a divisor of n and P is a divisor of this product, well then P must divide n minus the product of these prime numbers, which is actually 1. So then we are seeing that P must be dividing 1. Well, this is contradicting the fact that P is a prime number, and a prime number isn't something that can divide 1. So we are getting a contradiction. So our assumption that there are only finitely many prime numbers leads us to a contradiction, and therefore that assumption must be wrong. So there's got to be infinitely many prime numbers. Okay, so this is a set of exercises, so I'm not going to go over that, and I'm going to stop my video here. In the next video we will be looking at the least common multiple.